going to give you an update really on what we've been doing in the last 3 years. It was 3 years ago that I gave my last seminar in the department here. A lot has changed in that time. We've been successful with our project. And so instead of rehashing old ground, I'm going to give you the story so far as an up-to-date one. And you'll see from my talk that we have a couple of different areas of research. So I'm really going to give a 30-minute talk and then a 20-minute talk back to back. The title is fairly nebulous and it combines all the things we're interested in doing. But I'll give you a reminder, or I'll fill you in on what we're interested in doing in my group. We have 3 areas of research that you can define separately, really. We firstly work on microwave synthesis of metallic nanoparticles. And we're interested in making heterogeneous particles, heterogeneous catalysts that have unusual structures. And we can do that by using microwave synthesis. That's really our contribution to this field. And we can access compositions of particles like core shells and alloys that haven't been made before. So we can access unusual alloys, and I'll tell you some of their chemistry, tell you about some of their chemistry in a bit. There's some representative publications here. We also make mesoporous inorganic materials, and really one of the reasons for doing that is because we want to have something in which we can deposit these particles. So we make composite catalysts, and it's well known in heterogeneous catalysis that you want to do that. We want to make a composite where there's some synergy between the support and the particles. But there's also other reasons for doing this. These materials have many other applications. They're very high surface area. They have pores that are between 1 and 10 nanometers. You can see this on the TEM. So the particles are now sitting in here. And we've studied in collaboration with the Moths group and also with the Stevenson group using these as battery electrodes, and they seem to work very well in certain circumstances there too. So you can see we've made cobalt oxide, mixed perovskite oxides, and this stuff I'm not going to tell you about today, but I just had a little snippet on the first slide to show you we're doing that. And we also make microporous coordination materials. So whereas I said these have pores that are about 1 to 10 nanometers, we make materials that have pores that are more like 1/2 to 2 nanometers. And because these are much smaller, they're very good at selecting for small molecules like gases. And they have extremely high surface areas. And as you'll see, we can construct these nicely by using some synthetic chemical approaches. Our main addition to this field and the MOPS field, which I'll explain in a moment, has exploded in the last 20 years, become very competitive. But we've become known for using phosphines to make these materials and to be able to do some chemistry inside of the pores that you couldn't do otherwise. And so, again, there's some representative publications here. So I'm going to talk about this first, then I'm going to talk about a story based around this. And I'm just going to pick out a few stories from each area that will make sense and give you a flavor of what we've been doing. Okay, so by way of introduction into MOPS, for those of you who don't know what a MOP is, metal organic frameworks. This is an area which is not only flooded with researchers now, but also flooded with 3-letter acronyms. As you'll see as I go through, you have to have a 3-letter acronym to be cool, so we've got our own one that I'll introduce to you in a moment. But these are really, a MOF is really a coordination polymer. And so these are constructed a bit like Meccano or Lego in solution by taking inorganic nodes, which are really metal ions or clusters, and they're Lewis acids, and connecting them to organic linkers. And these are Lewis bases, and so we make coordination bonds between the metal and the ligand. The coordination bonds are easy to control based on the way the metal wants to bind to the ligand. And although this is very cartoon-like, you can see if you have a functional group on this linker, you can dangle that into the pore. So now we construct a porous polymer, and anything that enters this pore, a guest molecule, is going to see these functional groups. And this makes these materials more flexible and more designable than a zeolite, a naturally occurring porous material, because we can decorate the cavities of the pores. And so with a little bit more chemistry in mind, here's another scheme that explains what's going on. Here's a simple ligand, a benzene-based ligand, with 2 acid groups parallel to each other on the ring, and then one substituent that if you get the chemistry right and use the right kind of inorganic nodes, you'll only get bonding between these sites, not this one. And so you can make a porous material, which is crystalline, so it's really easy to study by X-ray diffraction. We can understand everything about the structural characteristics of the material. And you've got these nice groups within the pores that allow us to control the host gas selectivity. So if we compare these to zeolites, you can see that pore size and topology, chemical properties are much more tailorable. if we just make a good choice of the organic building blocks. The surface areas in these things can be very high, 6,000 square meters per gram plus, which is incredible. It's like a gram of the material has the surface area of a football gridiron, so you can do a lot with a small amount of material. And because we're making strong coordination bonds, you can get materials that are thermally stable over 500 degrees. So they're very applicable, and they could be used as replacement technologies in industrial processes, such as separations of molecules and storage of molecules. And also, if we want to change the characteristics of the material, it's a simple approach that means the geometry of the organic linker really ends up being transferred into the geometry of the material. So if you take a linear linker, you get something that looks cubic with the same inorganic nodes. If you take a trigonal linker, you can make something that has trigonal or hexagonal symmetry. So this is how we control and think about how to build these materials. So in the last 15 or 20 years, there's many works that have targeted certain applications of MOPS. It really started out with hydrogen storage and CO2 capture, and I think the jury's still completely out on whether hydrogen storage will ever work in these types of materials, just based on the economics of making enough of the materials. But this all came down to the fact that during the Bush administration, everyone wanted to study hydrogen. Then under Obama, everyone wanted to study CO2, so all that happened was people kept doing the same chemistry and changed the introduction section of their grant proposals and started talking about CO2. But these materials do have a very high uptake of CO2, and they work extremely well, better than zeolites. You can also see maybe something that's industrially more useful. They're very good at separating gases, so you can take a mixture of different fractions of gases and small molecules, and these materials can be so designed that they can selectively separate and absorb only certain gases over others. I'll show you some examples of sensing today. You can change the colors of the materials and use light-based properties to study what is inside the pore. People have tried these for drug delivery. I wouldn't want to swallow a lot of the metal organic frameworks that are available on the market, so this one has limitations in it. It obviously has to be biocompatible. But there are still lots of questions to be answered in this field, which is what we're trying to play a part in. And one of the questions is related to catalysis with these materials. And so we're really limited at this point by how much chemical reactivity we can engender into a metal organic framework that we can have inside the pores to allow us to do advanced reactions such as catalysis. And the problem is really that when you assemble one of these MOFs, and we do this in solution, most of the bonding and the chemical reactivity is taken up in the formation of the framework. And so keeping some behind, having some latent reactivity, is fairly difficult. You need to think about strategies to do that. This is like a dream idea from MOFs which hasn't really been realized yet, but you can think of a situation where you have an unrefined mixture of reagents that may actually be wet and in the presence of oxygen. Instead of having to refine the materials, purify them to stop it killing your catalyst, for example, you can have a material, a MOF, that is not only catalytically active, but it selectively only absorbs the molecules you want to react and excludes the ones that may kill the catalyst. And then you would get pure products out. So this is something which we can think of heading towards. And obviously this would cut down the number of processes in a chemical reaction by several steps. So what we do is use phosphines, as I said, and our acronym, which gets us in the club, is a PCM, which means a phosphine coordination material. And it really is descriptive, actually, of what we're making. We're making coordination polymers based on phosphine ligands. We like phosphines in particular because you've got this very loose basic lone pair that allows you to do lots of chemistry inside the pore. And so here's an example of how we do this. We first have to make a phosphine ligand. And this is one of the reasons why many people in the MOF field don't easily compete with us, because they're not willing to do the synthesis of tricky ligands to begin with. They want to shake and bake. We want to make some nice ligands to start with. And so we're making things that look, to all intents and purposes, like triaryl phosphines, but they have ancillary acid groups that we put in particular positions that allow us to react with a metal that's hard enough to only react with these acids, and will leave the phosphine alone. So now we make a polymer that's crystalline. We can analyze by X-ray diffraction, and you can see inside the pores we have free phosphine sites. So what we've done is made an ordered 3D polymer of a phosphine ligand. And it has these abundant phosphine sites that we can then do post-synthetic chemistry and attach things and tether things into the pores. Why is this good? Instead of making a whole library of MOFs for different purposes, we can just make one moth, and we can post-synthetically change it to whatever application we're interested in by using this phosphine as a handle. And there's an extra plus, we can do pre-synthetic organic chemistry, so we can plug things onto the phosphine sites beforehand, and then we find if we use exactly the same metals and the same conditions, we make completely different materials because we've already done the chemistry in a different order. So we get lots of different opportunities for these things. The stumbling block is making these, but they're the means to an end to get to our materials. All these phosphines, as you can see drawn, are also trigonal, which is great because it means we make porous materials that are three-dimensional and not 2D layered solids. And a lot of people in the moth field make 9 out of 10 layered materials and just don't publish 9 out of 10, only publish the porous one. We don't end up with that problem because these are so sterically encumbered that they always make 3D frameworks. And the organic synthesis we do has to be done on a fairly large scale so we can get at grams of material. I'm not going to go through much organic chemistry, just to show you one slide that proves this is modular and that we can take this chemistry as far out as we want. We do the chemistry to make these ligands by simple lithiation of cheap reagents. And this is important because if you want to scale these up, obviously the precursors have got to be fairly cheap and readily available. This gets us to these intermediate phosphines that have, for example, bromo groups wherever we want them. We can lithiate those again, turn them into acids. Then finally we take this ligand and react to make a polymer. And then we can do the crystallography and we can start to do some chemistry with the material. This is modular enough that by known organic routes we can do the same kind of approaches and make asymmetric ligands. Why might we want to do this? Well, this obviously allows us to make bigger pores of different shapes, and we can therefore pre-synthetically tailor our material to a certain application. Okay, so in one slide, here are some applications we've already studied without spending too much time just to show the diversity. We can take phosphine oxides, and these make very highly coupled materials because you can also couple through this PO group. And we've shown this material, for example, is useful for separation of alkanes that can't be easily separated by distillation. So we can do this by size, cyclohexane versus hexane. We do a lot of work with lanthanides, and one of the things that comes from this is unusual materials with metallic clusters that are interesting for their solid-state magnetism. I'm not talking about magnetism today, but this comes from my PhD, which was all magnetochemistry. We were interested in studying the solid-state magnetic behavior of these materials, and they're very useful as models. We can make chiral materials, which is more unusual in the metal organic framework field, and we can do this by making our phosphine chiral. Remember, all these examples I'm showing you are because we're using phosphine and because we're not just taking a regular ligand from the catalog. So this is how we can get at these materials. This one separates CO2 from all these other gases. And this is really where we want to go. We want to make catalysts, and we've shown that you can take a material and you can plug unsaturated metal sites inside the pores. So now what we've done is really back to front in a reverse route, made a polymer of an organometallic catalyst. Why is that good? It's insoluble, it's crystalline, so we could easily extract it from solution. The shapes of the pores allow us to control what can access the catalytic sites. And so really this is a way of making advanced catalysts that are hybrids. And in this case we've already shown, for example, that it could separate hexene from hexane by binding hexene at these sites. And so now some more recent things to show you the scope of these materials. This is all new work now. We've taken a material, this is Anna Nunez's work, she's already graduated and left Austin, but she worked on a material based on calcium, and this little microscope image is just to show you and remind you that all the materials are crystalline solids that are air stable. So once we make the material, it's completely air stable, we can handle it on the bench in air in different solvents. And if we take this material and try and do chemistry with it, we can expose the crystals to different reagents, like this. This is just a small map of some examples. To put metals on the phosphines, to oxidize them photosynthetically, to protect them. We can even do this methylation. These all happen at room temperature. And whether you're familiar with this chemistry or not, the interesting thing here is that if you make one of these p-alkyl head groups, we incorporate a counterion to balance the charge. And now we have an easy way to do anion-cation exchange in the materials. And so we can exchange, in this case, these anions and put fluorinated anions inside the pores, which gives us non-stick character. So again, the same one material has given us access to 7 or 8 new materials. And we study these carefully to see how the properties of the materials change as a result of what is inside the pore. And so one good example, as I told you, CO2 sequestration. We look at the binding energies of CO2 in the materials. So we're interested in how the CO2 molecules are interacting with the inner surfaces of the pores and which types of groups are more useful. So here, this is the parent material, the white data. And by adding different groups to the pores, we can tune positively or negatively the average binding energy of CO2. And that's good because if you want low capacity but easy regeneration, you want to be down here, low binding energy. If you want high capacity in which the CO2 is more strongly stored, you want to be up here. And so we can tune pretty broadly just by doing one simple photosynthetic adaptation. We did also look at things like hydrogen uptake because it was cool at the time. And you can see by adding unsaturated metal sites, for example, you can greatly increase the uptake of small gases like H2. This number is one of the highest known for a material of its type. And this is at room temperature and 1 atmosphere. So you can see we've got about 16 hydrogen molecules per cavity. So we're really packing a lot of H2 into the material based on the fact that it stacks around the unsaturated gold sites. And maybe this is industrially most useful. You can really improve the separation properties of a material. This is again exactly the same material, but when we fluorinate the cavities, you can reduce the uptake of certain gases at the expense of others, and this now becomes a completely selective CO2 sequestration material just because the cavities are fluorinated. So that's some examples of what we can basically do with these phosphine materials because we have phosphorus as a reactive site in there. We've also taken this more recently to sensing applications. I'm going to fly through one example and then show you some new data that we haven't published. This is an example with terbium, where we take the same phosphine ligand, in fact it's oxidized in this case. We make a very rigid and highly porous framework. And this is where crystallography, again, is very important. You couldn't get this from an amorphous material. We know that every single metal site that forms the polymer has these 8 groups attached to it, but one of them is a water ligand. And you might think that's surprising that water's in there. We actually make the material in water, so there's water and a couple of other solvents. That's good because if you can make anything in water, it's going to be stable in water, and that's an industrially important question. How stable is this in ambient air, in moisture, and so on? And there's really water in the framework. And moreover, we can pull that off under vacuum. And you can see in a single crystal fashion, and I'm going to show you some more of these. It's cool that you can take a single crystal, glue it onto the diffractometer, heat the crystal up and see something change without the crystallinity being lost. We see this water disappear, but you see the structure hasn't changed. Now, if this was a molecule and you removed one ligand, all of the other ligands would move around to take up the spare space. This can't happen in a framework because it's rigid, and so we have this open receptor site that we've generated on every single metal, and it sits inside the pores. It's completely reversible. You can put this back on with steam or vapor, and you see if we do a measurement which is representative of the bulk to make sure this is working in the bulk, you can see the crystallinity of the material is completely intact in either state. Nothing's happening apart from the single water being removed. And if you look at the luminescence of this material, and this is because the terbium itself is emissive, you can actually monitor which state of the material you're in. Now I have to explain a little bit quickly about the luminescence here, not in too much detail, but these materials are luminescent, strongly luminescent, because the phosphine ligands themselves that make up the walls of the material absorb light. They get to an excited state. They transfer the excited state energy to the lanthanides, which are also within the framework. The lanthanide is now excited, so it's been indirectly excited, and it luminesces. It decays by luminescence. Now, if you have water close to the lanthanide, or some other groups, certain bonds, like OH bonds in water, quench luminescence, so they're bad. If they're close to the excited lanthanide, you get non-radiative quenching. And so we know for a fact, if we're in this state, the luminescence is low, and then it doubles when you remove this water. Well, you might say that's okay, we've got a handle to describe what's going on in the material, but it's more useful than that, because we can start putting other solvents back inside the pores and seeing how they affect the luminescence intensity. So you see something like ethanol, which can get close to that lanthanide and bind to it and bring an OH bond close by, also quenches, but something like toluene doesn't quench at all because it just sits in the cavity. We always check to make sure that the solvents are inside the pores. So this is vapor sorption to show that the materials are always loaded. And we did this with a load more solvents and vapors and looked at the change in the luminescence, again just to show you that these materials completely retain their crystallinity. In fact, we went for a whole gamut of different small molecule gases and vapors, and based on the difference between the luminescence intensity or the quantum yield of the activated material versus the parent material, we can see there's a fairly gradual change based on the degree of quenching that each one of these guest molecules inside the pores will incur on the material. And it makes sense, for example, that if you look at ammonia and water, here the ammonia is a small ligand that sticks to the terbium. It has statistically more NH bonds than OH bonds, so it's a stronger quencher. And you can use this to discriminate between different species. Now, we patented this and spoke to some companies that are interested in online sampling. And one of the things they're interested in, for whatever reason I can't really explain, is things like ammonia in pure hydrogen. And so we can take the material, load the material with hydrogen gas, there's no quenching, start to dose in very small amounts of ammonia to emulate some impurity, and if you integrate the area under the peak, you find this is completely linear, so we can use this as a diagnostic way to back calculate, for example, how much ammonia there is inside the hydrogen gas stream. So this works pretty well for other combinations of gases we've tried as well. And on the back of this, we tried to make more lanthanide-based sensor materials. And this is some new unpublished work that Sam Dunning, who's currently in the group, and Alan Nunez, before she left, she actually found out about these materials to begin with. These are based on the similar ligand. Again, look, we've got phosphines here, and we're taking lanthanides. In this case, we can make the material with basically every lanthanide we want. It's completely non-selective, so the material will always form this way. It has these really big hexagonal pores, so it looks a bit like an eclipsed version of graphite. And this is interesting because it is a layered material. So in the crystal structure here, I'm showing you a layer that's packed next to the next layer, and you can see alternating layers are very tightly stacked against one another. And they're lined up in an eclipsed fashion, so you get an infinite 1D tube going through the material that you can put guest molecules into. Normally things want to stagger, just like graphite does, because they want to maximize their interactions. There's something special about this material that allows it to eclipse, which I'll show you. And because we can put different lanthanides into the material, we can get different emissive colors in this case, and that can be useful for diagnostics. And this is why the layers are eclipsed. It's because between each sheet, and these are bonds between the layers, as shown in these green dashed bonds, we have very close range, a multitude of strong hydrogen bonding interactions that keep everything pinned together. Now, because I showed you on the previous slide we can remove the water, you find that when you remove these, all the layers start to shift because there's nothing now to pin them together. And you can see this in the X-ray diffraction. You can see a change in the cell parameters, and this is reversible. And we know that if we take the material and remove the solvent, everything collapses, and it looks like the material has died. It's like it's gone to crap. There's no more luminescence. But if you expose it back to solvents, you completely recover the luminescence. So once the solvent goes back in, it forces all the layers to line up again. And we can see this in the bulk. You can see your crystalline material looks like it's completely amorphous now. And as soon as you're exposed to different solvents, all the crystallinity comes back. So this is it's a solid state reversible transition. We photographed the crystals of this material in the process over several days to make sure, to answer the question, this is not something dissolving and recrystallizing, because that would definitely be cheating. The crystals don't go anywhere, it is all inside the crystals. And this is, again, because we have phosphines, we can do chemistry that other people would not be able to do. We can take the solid crystals, expose them to concentrated peroxide, and it doesn't digest the crystals, it just simply targets the phosphines and oxidizes them. And this happens in a single crystal fashion. So we dip our crystal in peroxide, put it back on the diffractometer, and now we can see all the phosphine oxides. It's done nothing to the structure of the material, but it's done something electronically important. What it does is increases the quantum yield to nearly 90%, which is about as good as you can get with these types of materials. And you can see all we've done is added this oxide. Now the reason it's increased the quantum yield is because if you look at the triplet state of the free phosphine or the phosphine oxide, you can see there's quite a difference in the energies of the excited states of the ligands. And so really we're optimizing in the solid state the excited state energy of the ligand to match the lanthanide and get a better energy transfer, a more effective energy transfer. And that's only because we have these phosphines that we can do this. This is a chemically reactive species that allows us to do this. Why do we want to do it post-synthetically? Why don't we just do this before we use the ligand? You can't make the same material. That was the material I showed you previously with the pre-oxidized ligand. And recently, Sam has worked with Matt Moore in the Holiday group to show really how fast this material acts as a sensor. So you can see the phosphine is always lower than the phosphine oxide, but actually these things switch on within a few seconds, and the luminescence intensity levels out. Then you can reactivate the material, it switches back onto the same level. This is completely reversible. So what we're doing here is taking the crystals, we remove the solvent, they're now non-emissive. You just got this crystalline dark material. As soon as you expose a vapor or a droplet of solvent, the crystals light up again. This is completely reversible. So what can we do with that? Well, we can try and do selective sensing with it. So because we can use different lanthanides, the terbium version of the material looks green, the europium looks red. Sam has been able to mix the lanthanides in the materials, and you can see as you do that, you can tune the colors. So if we have one-to-one randomly distributed terbium and europium, you get something that's yellow. If you want a sensor which can give a different color light, you could start to mix in 3 or 4 metals, and we can go from yellow to whiter light or bluer emission. So we can play around with this just by simply thinking about how much of each metal we add in the precursors. And if we use non-emissive metals, this is just to prove to you that the ligands themselves are being excited. You get phosphorescence from the ligand backbone. This one's interesting. If we take this as a sensor, believe it or not, if you put it in the presence of different solvents, it changes color like a traffic light. And so we can tell if we have this material in something like dioxane, DMF, or water, just by simply exposing the activated crystals. And we can do this with other solvents as well. So it's like a color-responsive dipstick for solvents, and we're trying to now use 2 or 3 different combinations of metals in like an array, so that you can get a coded response to different solvents. So this all works pretty well. One of the other things I want to show you before I move on to the second part of the talk is about how we're trying to make targeted catalysts for PCMs. And this has been a really a hard synthetic battle, but we've actually finally got there. And we're now getting to the point where we can publish these kind of papers in the field that other people have been trying to publish and haven't managed to get at. So what we're doing here is addressing a problem that we found from our research, and that is that with these previous materials I showed you, yes, they're crystalline, very stable, but when we make the materials, each phosphine site, our important reactive site, is spaced at a certain distance from the next, and we can't very easily engineer the distance between the phosphines. That's what we need to do if we want to put a metal onto more than one phosphine at once. And so the phosphines are here, the metal can't use both of them at once, and we don't know how to get around that problem. Apart from doing more complex organic chemistry to make building blocks that are already engineered that way. And so the first time we did this is work that Alicia Bonzak managed to make work pretty well, is doing some organic chemistry to make these bisphosphine ligands. Without going through the organic chemistry in detail, this is pretty arduous, and there's several steps just to get to these precursors. Once we can get to this precursor, we can apply our same chemistry of lithiation, and we can make materials like this. Now, this looks like a ligand, to all intents and purposes, that many people have used in organic chemistry and in organometallic chemistry, but we've got our acid groups in the ancillary positions. So we can coordinate now a range of metals, and because this is chelating, it's a stable precursor building block. We can choose which metal we want to put in here for the type of chemistry we're interested in performing. The question is, and now is this a good idea for a project or a disastrous idea, because we've done 6 months of synthesis, can we go the final step, react with metals and make phosphine coordination material? The answer is, Alicia was very quick to do this, and yes, it works pretty well. So you can see here you can make molecular species that are crystalline. Here's the example I'm going to show you with platinum dichloride in this bisphosphine. We can make other species as well. All of these are based on the strategy that this ligand has been really popular in making metal organic frameworks with 4 carboxylic acids in this kind of pseudo-square orientation. And it just makes nice porous materials. However, in our case, we're making sure that our acids are in the same position once we've put a metal in there. But instead of having boring benzene rings that don't do much chemistry, we have these open metal sites. And so Alicia took the ligand, reacted it under conditions that suited the formation of crystals, and I'm not belittling this chemistry. We do have to make grams and grams of this often to find the right conditions to make a framework. And it becomes, unfortunately at this point, a little bit shotgun. But if you get the conditions right, you can react your species with metals that will polymerize these acid groups, make these incredibly high symmetry species, and we get this really ordered porous material with large oval pores, and in every wall you can see one of these catalytic sites. I don't know whether Vince Lynch is in the room, but Vince has discovered that the crystallography of these is very difficult, and we've struggled in many cases because the symmetry is so high that these things all do this in the framework. They can insert themselves in one of two directions. And so really this is completely disordered. The symmetry here is so high that these are back to front at random positions. When we look at the material, it has a high surface area. We do gas absorption to measure the surface areas. This has a decent surface area that means it's accessible on the inside of the material. At low temperature, if you're looking for catalytic properties, nothing is really happening, but this is a cryogenic temperature. And that's not necessarily so surprising because normally most catalytic reactions on organometallic species will run at higher temperatures. But what we did find, to our pleasant surprise, was that at higher temperatures, actually 150 degrees, we start to get H2 binding at the metal sites in the pores. And this hadn't been seen before in these types of materials, simply because, as you can see from these other sets of data, which are other known metal organic frameworks, the higher the temperature, the less the H2 wants to bind in the surfaces of the pores. It's just bashing around and getting kinetically too excited. We've got these reactive sites that grab hold of the H2, and some calculations since performed by a group in Berkeley have proven that it really is the H2 having an interaction with the pocket that's formed with this platinum or palladium site. We get trapping of the gases. We can also do, Alicia did some basic catalytic studies to show that these sites within the pores can be activated, and we can make these chiral intermediates by doing addition chemistry and making real metal carbon bonds. And the good news is, although I won't spend much time on these couple of slides, this is now a universal building block. Once you've done the chemistry to make the precursor, react with a different metal, in this case cobalt, we can make a different framework. Why is that useful? Because we can get access to different shaped pores. And so this is another material with the same building block in a different orientation. Here we have, I think, 4 different pore dimensions. And this one has cobalt instead of zinc in the corners. And these have the water groups again, because we're making them in the presence of water. And those can be pulled off, just as I showed you in the previous example. So now we have activated sites in 2 places, in the corners and in the catalytically active metals. And you can see this cobalt, for those of you who are good at inorganic chemistry, when you remove 2 waters, this becomes tetrahedral, and tetrahedral cobalt is blue, and you can see a reversible color change in the crystals. Okay, now the little last part of this story is that once this started to work and we started to get some nice results, I got a really good organic guy join my group, Jun Peng He, who was able to make a ligand which we wouldn't have probably managed to make otherwise. Again, I'm skipping through a lot of organic chemistry just to show you that he can make these types of ligands, which are so-called PCP or PNP pincers. If you know nothing about these ligands, that's fine. Just to say these are a very popular scaffold in organometallic chemistry because they engender a lot of reactivity into the transition metal site that you can put into these. So you install a group like this, and they'll do lots and lots of chemistry. Now the question is, if we make this and put acid groups on the outsides, and really this is where all the effort comes in, again, can we make a framework? Well, this is what the metallated species looks like by crystallography. It looks like the 4 carboxylic acids are in the right place. And this took a while. I don't know how long Jun spent trying reactions. Quite some time, but now he's made, in the last month or 2, 3 of these. So I know several people in the moth field are trying to get at these by a different route, and basically we're happy that we've beaten them. It's been a stressful process because I spoke to a few other people and they were trying to make PCP and PNP moths, but we've done it. You can see we've got these nice pore windows in the material. We've got access to these species built into a 3D crystalline polymer. And some of the reactions of interest, well, this PCP is known to insert CO2 into metal carbon bonds, and so this is where the project is going in the next couple of months. We're interested to see if we can use not only the material's ability to store lots of CO2, but also to react it in situ and insert into simple bonds so that we can use CO2 for useful chemistry and maybe make these carbonyl type species. The last couple slides on this area are a little bit separate, but just to give you a flavor for what we're trying to do in making water stable and very cheap and upscalable materials. This is amazing that this reaction works so well. A ligand that's a little bit cheaper and easier to make, magnesium nitrate, one of the cheapest metal precursors you could come across, potassium hydroxide, pure water as the solvent, nothing else, stuck in the microwave for 35 minutes, and out comes this amazing porous material, highly crystalline material. By crystallography, you can see all these yellow atoms are just water. They're filling these square pores. But this material has some very unusual properties. It's thermally stable, and this is a TPA trait up to 500 degrees because the metal ligand bonds are very strong. This is what the SEM of the crystal looks like. If you make crystals in 30 minutes in the microwave, they're always small, so you have to pay attention to that. But we can take these crystals again and heat them up on the diffractometer and see single crystal conversions, which are very surprising. So you've got this material that's porous, full of water. By blowing hot nitrogen across it, you blow all of the waters out. The pore changes shape. The whole crystal actually compresses because the pores are concertinaing somewhat because they're now empty, but they don't collapse because the material resists that by having this corrugated structure. And so now you can see the pores become more of a diamond and it's empty. And we can dip these crystals into a range of solvents, and the solvents load the pores. Maybe not surprisingly, but when I show this picture to most people, they think now this is a model because people are commonly modeling solvents in the pores. These are all single crystal structures. We take the crystals, dip them in the solvents, and then we can do crystallography again and find where the solvent molecules are sitting inside these pores, which is quite remarkable. What's more remarkable is that you can separate isomers completely. So if we take a 1-to-1-to-1 mixture of xylenes or divinyl benzenes, and this is a very important industrial separation, only the para isomers go inside the pores. And they do that because they can only stack in this particular orientation, which is head to tail. And so with these two, and we're working with a company that separates xylene on a very large scale in Houston to see if we can make the material. The only limitation is, can you make the material fast enough and cheap enough to put it in a moving bed where you need tons and tons of the stuff. But this has a much better separation than the zeolite loaded with barium X, which is what they're using for this process at the moment. And so we've looked at the uptake characteristics of this material by kinetics. You can see the para isomers push everything else out of the material, and the same is true for the xylene as well as this divinyl benzene. This is used to make Dow-X resin. This is what Dow uses to make Dow-X resin. Okay, so that's the first part of my talk, and I promise I won't run over time. The second part's a bit shorter. I've got an intermission slide, as it were, to show about this project that we're excited to get going. I've been trying to get funding for this for like 5 years and finally managed to break through and get funding for this, what we call another 3-letter acronym, the Austin International Framework. It's got framework in the name because it involves an interchange of students and a collaboration between different groups working in metal organic framework chemistry. It's great for undergraduate students because it's hands-on wet synthesis. And I've picked groups in these different locations who are well known in this field, A, because it helps me to collaborate with them, but B, because most importantly it allows us to exchange undergraduate students. And so we're starting this scheme up this year, and we're going to try and grow it each year, where undergraduate students from Austin will come into our lab, start to get hands-on with chemistry, then we'll exchange them for a year, and they can choose to go to Paris, for example, or somewhere in the UK or in Japan, or wherever they may want to go. Some people may even want to go to Windsor in Canada. And so, yeah, this is exciting that we're now getting this going. And that's on the MOPS stuff. Okay, so for the last 15 or so minutes, I'm going to tell you about our project on heterogeneous catalysis by metallic nanoparticles. This is much easier to justify to the audience than the previous stuff, because heterogeneous catalysis is just so widespread in all industry. And as you can see from the bullet point there, about 90% of all the chemical processes involve catalysts, and a very large quantity of those in terms of volume are heterogeneous, although obviously homogeneous chemistry, organometallic chemistry of pharmaceuticals and so on is extremely important. If you're thinking about the ground up from C1, from methane going up to bulk commodity chemicals, it's predominantly heterogeneous catalysis, and that involves metals that are expensive, and so being able to use metals in more effective ways, metals that are rare in the Earth's crust is very important. You see I've boxed in a few examples, and these are huge reactions, NOx reduction in every car, syngas, for example, cracking using zeolites. You'll see most of these catalysts, the common catalysts, involve an expensive metal and sometimes supported on a secondary material that gives a synergic effect. And this is important because you need, after starting to talk with industrial companies and really understand what is going on here, they want a catalyst that will last for 10 years and that they can make tons of rather than a few grams of. And so even if we think about very nice complicated catalysts, it all comes down to how much of it you can make at a certain cost. And so metallic nanoparticles, which are really fancy colloids, have become extremely popular in recent times because if you can do the synthesis of them from a bottom-up approach carefully, you can control the selectivity of the particles. And the reason why this is important is that although heterogeneous catalysts are very easy to maintain and recycle because they're always in a different phase, a problem with these catalysts is selectivity because they're metal surfaces and the selectivity is lower than a well-designed single-site catalyst. And one way to improve upon selectivity is to control the surface ordering of the atoms, because in a crystalline metal you can have different atom arrangements or packing on the surfaces that are exposed in different ways. And it's well known from many surface science studies that a single metal that's a pure crystalline metal can have a different reactivity for a simple reaction based on the type of metal surface that's exposed. And that's because the packing density of atoms on the surface is different on different lattice planes. And so that results in changes in the chemistry. And so here you can see there's a rhodium particle that's anchored onto some oxide material. This is very useful because you've got a lot of surface area and not much volume. And that's important. We want to use as much of the metal as we can. If it's heterogeneous catalysis, it's only the surface that counts because it's only the surface that's exposed. And so our thinking in this is to grow particles that have very defined properties, both composition-wise and structurally, so that we can try and improve upon existing catalysts for simple reactions. Now, these are simple reactions that you shouldn't belittle just because we're doing hydrogenation of simple alkenes, for example. If you have a chiral catalyst that can do a fancy coupling or a fancy hydrogenation selectively at 1 of 15 CC bonds, that's good. But in this case, if you want to be able to do thousands of tons of reagent to conversion to products in a day or a year, this is the way you have to do the chemistry. And so metal nanoparticles, which I'm showing here this is a cube octahedron, and they're very useful because there's a large surface area. Corners and edges are very reactive because they're very exposed, and so they can increase turnover efficiency. And all of the metals that we're interested in, which come from this part of the periodic table, are really FCC in terms of their lattice structure. They're face-centered cubic. And so they'll pack in this type of arrangement. And remember I said you've got to control the surface chemistry because a square face is less densely packed than a triangular face. This is like packing pool balls in a pool triangle before you start a game. This is a less dense arrangement, and so the binding chemistry is different on these faces. So if we can control the chemistry kinetically, and for example only grow on triangular faces, you should end up with cubes that have more selective chemistry on their surfaces. And conversely, if you grow on square faces, you should get octahedra and tetrahedra, which are equally selective. This is a challenge, though, because you've got to do this in solution by adding atoms one by one. And really what we're trying to do is, instead of having to go the top-down approach, which is taking a crystal and mechanically grinding it to a certain shape, which means there's a lot of wasted metal under here, we're trying to do this from the bottom up in one step. And then we deposit them onto or inside a material that makes our composite catalyst, and then we can study them. Now this is our main contribution to this field in the past few years, is the use of microwave synthesis to change this chemistry. And so we adapted a microwave reactor in which we used regular glassware so that we could directly and carefully compare the effects of microwave heating versus conventional heating and nothing else different. So we would physically take the glassware out, use it in all of that, do the same reaction in the microwave cavity. This is one of these scale-up acid digestion microwaves, and the good thing about microwave chemistry, if it works on a small scale, you can scale it up to flow chemistry, and it works on a larger scale. And we also control the addition of our molecular precursor using a syringe pump. And we did a couple of years of exhaustive work on the conditions, and now this is just robotic, reproducible, works every time. So for example, we fire in a small amount of precursor to begin a seeding process, then we may change the addition rate, which is all controlled by the syringe pump, and this allows us to kinetically control the shapes of our nanoparticles. Now the one thing I'm hoping to convince you of is that the difference between microwave heating and conventional heating is large, and it's all because the heating is a completely different mechanism. So if we take a polar solvent and we have to use polar reagents, they strongly couple to microwaves. The heating's more inside out, which is why you put a pie in the microwave and you heat it up, you can burn the inside of your mouth because the outside's cold and the inside is really hot. In this case, if we use polar solvents and the reagents themselves, the atomic species are very polar, they couple to the microwave heating and they dissipate heat very rapidly in small spots, and these are called by the microwave chemists hotspots. And these hotspots can be several hundred degrees hotter than the bulk temperature. So the bulk temperature may read 150 degrees on a thermometer, but you've got areas in the solution which are short-lived, but could be several hundred degrees hotter, and they're really nice nucleation sites for making nanoparticles. And so we've kept the chemistry simple in that we want to make this universally applicable. Simple metal precursors, rhodium, platinum, palladium, iridium, simple, cheap organic polymers, and simple, cheap solvents. So nothing special. We haven't played around with the precursors, but using microwave synthesis to really see the difference. And we saw initially in this initial work a couple of years ago that under conventional heating, if you did this addition of rhodium to the solution, after just 30 seconds, you get these very poorly formed clusters that are really polycrystalline, and they have nothing going for them that's good. If you do the same reaction in exactly the same glassware in the microwave at the same bulk temperature, you see there's a huge difference. We make fewer larger particles. After 30 seconds, they're already highly crystalline. We can see by high-res TEM that they're very ordered. And this tells us that the nucleation and growth occurs very quickly. We make this burst of particles, and we can get better control here. Now, if we then add more precursor at a rate at which means we only grow on the existing particles and we don't create new particles, you find that under conventional heating conditions, on the left-hand side here, unfortunately these small particles that are a mess become bigger particles that are a bigger mess. And so you've got no selectivity over the surfaces because we've got lots of jumbles of shapes, and so therefore you've got all of these different surfaces exposed. Whereas in the microwave case, we can make well, you can see this very well, but we can make a majority of tetrahedra, or we can make a majority of cubes. This works with about 90% selectivity, which is pretty good in this area, by using the microwave heating. And again, these particles, when you look at single particles from the microwave, are much more highly crystalline. So it's faster, and it makes more effective particles, which is all we were looking for. You can also dial in the average size of your particle simply by how much precursor you add. So it's completely simple at this point. Just very quickly, I'd like to show how we do the catalysis, because for those of you who are used to doing solution phase, this is not solution phase catalysis. We have a home-built reactor where we mix reactive gases using mass flow controllers. We pass them through a heated line. Here's our organic reactant. Today I'm just going to show you alkenes, cycloalkenes. They then pass through a heated line straight through our catalyst, which is on a frit. It's a single pass. Everything goes, all the reactants go across the catalyst. The products are vented into a GC, and this is set up with pneumatic control so that every 2 minutes it takes a new injection, so you haven't got to sit there pressing the button. And what this also means is we get kinetic information. So we can see how the catalyst changes over hours or days. And we're using a tiny amount of catalyst. This is 10 megs of catalyst, which is 1 weight % nanoparticles when we deposit these. And so this is a really tiny amount, nanomoles or nanograms of the metal. This is how we make the catalyst. It's pretty simple. We take our particles, we deposit them on silica or whatever other substrate we're interested in. This stops them agglomerating, it dilutes them, it allows us to handle the material. And we found out early on that when you normalize everything and you look at hydrogenations of alkenes, which is, as I said, a very important basic reaction, you see that the microwave prepared particles are about twice as active as conventionally prepared particles. That's because the surfaces are cleaner, they're more crystalline, and you just get better turnovers. And you can see this played out in the activation energies on the surfaces. So then we took the chemistry further, and this is again newer chemistry that I haven't shown people before, but we started to try and make core shell particles. The reason for doing this was because we thought by using our microwave heating method, we'd have ways to use sacrificial cores and just grow thin shells of reactive metals on top. And this works. We've done this for both gold and silver cores and reactive shells. I'm showing you an example with gold here. Bear in mind that silver as a core is industrially way better because silver's much, much cheaper than gold. But for hydrogenation chemistry, remember, neither silver nor gold is active. And so whether you use a gold particle or a silver particle, it's going to be useless for hydrogenation. What we want to do is grow a thin shell of a reactive metal, in this case rhodium on top, and have that be therefore a reduced amount but still a reactive species. And also by using this synthetic means in the microwave, we can change the thickness of the overlayer and see how both electronic and strain effects might play out. And what I mean by this is there's obviously electronically going to be an interaction between the core and the shell because they're different types of atoms. And also, as you see stated here, there's a certain lattice mismatch between the core and the shell. So even though these two metals, in this case silver and rhodium or gold and rhodium, have the same packing structure, the interatomic distances are slightly different. And so when you try and lay the first layer of a new metal on top of the core metal, if the distances of the atoms are being skewed, and that could either be compressive or expansive, the metal's not very happy, and it can undergo some changes, which will mean its catalytic properties are different. So we can assess this by making thin overlays. You can see the particles just get bigger as you grow them. And we saw, to our delight, that these are very active catalysts. This is the hydrogenation activity of gold cores as a test. They're dead. This is the hydrogenation activity of rhodium particles, and these are our rhodium core shells with gold in the core. So you can see they're much more catalytically active. They take longer to reach steady state, and that's because there's some rearrangements going on, and the shells are a little bit strained. This is a cartoon of what you can think is going on here, and the silica is just the support. And we know for a fact that from measurements like XPS, there is also a difference in the oxidation states at the surface when you have an electron-rich and electron-donating core, such as gold in this case. We did the same for silver, and this is work that Stephanie Garcia, who's now working for a nanotech company in Houston, worked on. And you can see that, again, if you have these core shells, they're much more active. Now, one experiment, and this ends the story, and I've got like 4 or 5 slides left and I'm done. One thing we wanted to prove, and it's important in this kind of field, was that when we do catalysis, the core and the shell were not inverting. And there are many examples that are known where you take a core shell particle, you heat it up, you do some chemistry, it'll invert. The core will migrate to the surface and push the surface inside. The easy answer to these problems for rhodium silver and rhodium gold was that they're classically immiscible. No alloys of those are known. And if you look at the phase diagram, you've got to heat the two metals to about 1400 Kelvin, then they'll alloy, but they're like an alloy melt. As they cool, they phase segregate, and this is because the binding energies of the pure metals are favorable over the binding energies of the alloys. So you can't alloy them, they're just an unknown, unstudied alloy. So the test I thought was a good idea to give Steph was, why don't you just inject both metals at once into the microwave cavity, and because we're now not taking a core and overlaying the shell, you're just going to make pure rhodium and pure silver, or pure rhodium and pure gold, and we've proven that you have to do it this way around. Well, she did that, and she's very diligent. She was great in the lab, fantastic student, and she came back and said, all the spectroscopy says they're alloys. No, these alloys don't exist. But sure enough, in the microwave, and you can't do this conventionally, you can make alloy nanoparticles with random structures with these combinations of metals. They are stable on the nanoscale because presumably something unique is happening on the nanoscale that's allowing them to be metastable. If we grow them big, 30 or 40 nanometers, they phase segregate, which plays along with what you would expect classically. You wouldn't want particles that big because they're just useless at that point anyway, but we can make very stable particles that are 5 to 10 nanometers in size and do chemistry with them. We can also tune the composition widely just by the amounts of metals we add, and you get these amazing alloy particles. And so we started to do catalysis, and I realize I'm 4 minutes from time, so I'm going to skip through this characterizing data, but just to show the XRD shows a shift, and the surface plasmon behavior of these particles is unusual, telling you that there is a random alloy in mixing. So you take it from me that these are random alloys, they're not intermetallic and they're not ordered. When we did some hydrogenation chemistry with these, again, gold is dead. Here's our rhodium for scale. We found that all of these particles were somehow more active than rhodium itself, which didn't make too much sense to begin with because you're diluting the rhodium with gold, and gold's inactive in hydrogenation, so why is it making a more active catalyst? We can see the interaction between, or the correlation between composition and turnover. And you see that you still need more gold you still need more rhodium than gold to get active catalysis, but they are pretty good catalysts. And even more so, and this is our favorite alloy by far, rhodium silver. You can take rhodium, very expensive, dilute it down with silver, and make an even more active catalyst than you started with. And we found here that this is way off scale. You've got rhodium down here, and then as long as you've got a fairly rhodium-rich particle, rhodium-27, silver 73 up, you get very high turnover numbers. And so this is the point at which Steph and I knew what we'd got, but we were stuck, and I went to Graham Henkelman and tried to convince Graham to collaborate with us on this, and Graham's really a popular guy, and so many people wanted to collaborate with him. And he probably looked at me to start with and thought, well, you've got rhodium here, you've got silver here, aren't you just making synthetic palladium in the middle by alloying one-to-one? And so we ran some palladium particles, and sure enough, the palladium particles are kind of down here. So something really was going on with these alloys. Again, here's the bell curve that shows you could be around 50%. I'm going to put these two together. I've got the last two slides now on what Graham has helped us with. You can see that you can have rhodium-silver alloys, and they're so much more active than pure rhodium particles for simple hydrogenations. So then Graham went away with his guy Liang and did all these nice calculations, and we come up with this, which I think is a very good explanation of what is happening. And they've modeled the reaction through all the important steps. So we've got a pure open metal surface, adsorption of the alkene. I'm explaining this because it's hard to see. Co-adsorption of the hydrogen, so that the H2 splits to give these two purple atoms, which is the two hydrides. One hydride migrates, the second hydride migrates, and then this step is important, it's desorption of the product. If you can't desorb the product, it stands to reason you can't get more reactants down, and that's one of the rate limiting steps. And the good thing with this model is that we now don't assume one step in particular is rate limiting. Now they calculated for all of the FCC noble metals, and you can see rhodium in black has the strongest binding energy all the way down here, which is great, because it means you get everything stuck on the surface. However, now it's a problem because rhodium is very reactive, it can often chew things up. It now doesn't like to release the reagents, it doesn't like to do chemistry. Whereas silver, which is in red at the opposite end of the spectrum here, is useless at binding things. In fact, it can't spontaneously absorb these reagents, but it's very good at desorbing them. And so I think a good way of thinking about this, at least for me as a synthetic chemist, is you've got a random surface. The rhodium sites, and Graham can argue with me if this is not the right way of thinking about it, but the rhodium is doing chemistry. Nearby you've got silver, which is helping to desorb the product, so you balance the two. And in this psychedelic plot, you can see rhodium is the strongest at binding both. Silver's up here, the weakest binder. And if we extrapolate a line between the two, it does look like the best balance would be a one-to-one alloy, which goes along with what we've seen. What Graham hasn't seen is that we've started to try and probe this with other alloys we can make. Here's a palladium gold alloy, so we've put a new line on the diagram. And again, it correlates pretty closely. We see that about 70% palladium is the most active. This is work by Prano in my group. And that does get pretty close to the center of the line. So we've got a lot to do with this now. We've got some money to work on this. We can make alloys with 3 or more metals in the structure, and we can dilute expensive metals and make more active catalysts, which is good. Okay, with 2 minutes to go, I have finished. I haven't got conclusion slides because I wanted to show more data than conclusions. This is obviously the most important slide I have. I thank all of my group for all of their great efforts over the last few years. This is a picture from the pool party last year. The people in bold are the ones on the picture. And I went through all of my past annual reports and got all the names of all the undergrads that have gone through the group as well, so that I hopefully haven't left anyone out. It looks like I've had a huge war effort. Fortunately, most of these are undergrads at the bottom here, so they weren't all grad students at the time, but a lot of people have played important roles in this science. That said, there's also another acknowledgement slide. I wouldn't normally use this when I go around giving a talk, obviously, but it's important in this instance to recognize all these people who have played important roles the Hengelman group and the Crooks group have been very important. Dr. Zhongshan Chang is the guy who does all the vapor absorption measurements in Korea, is very important. Collaborate with Brad Holliday and his group on the luminescence. Some, with Buddy on the batteries. I haven't talked about inelastic neutron scattering work that we're doing with a couple of groups at Los Alamos and USF, but that's going well. Also magnetochemistry and some electronic measurements. So there's more to talk about in the future. And I really want to say thanks to Vince, because he's been an amazing help to us. Also Steve Moore, John Baxendale, and Betsy and other people in the department who keep things running are very important as far as I'm concerned. And these are some other important people who help us make measurements. This is all the funders, the money we spent or are spending. And I'm going to finish again on this slide because it's more important. And thank you for your attention. I know I've only got a couple of minutes for questions, but I'll take any that you have. And thanks for coming to listen.
Okay, thank you so much. The floor is now open for questions, discussions.
For the core shell particles, do you have a sense for how thick the shells are?
Yeah, so we've measured them by, well, we've measured them by 2 or 3 different ways and tried to compare the measurements. So you can just do the average size increased by TEM and come up with a number that suggests how many monolayers you've added. We've also done some cross-sectional imaging. What we can't tell is whether the shells are completely uniform throughout. So I was really drawing those cartoons of how I think they should be represented. So there's lumpy bits on the surface. What we do know is after catalysis, you don't get any balling up so that there's core that's actually exposed. And so it's the number of monolayers we're quoting is the average across the bulk. If you look at individual particles, there are no naked particles that haven't been coated.
So what are the typical numbers, or do you have control over?
Yeah, it's just how much we add. We can't get much lower than 2 monolayers. It would be great, I think Graham would be interested if we could make a single monolayer coating. It's just difficult. By about 2 monolayers it's stable. I think with 1 monolayer we get wholly lumps, and then we can go big. So we've compared, say, 2 to 4 to 6 monolayers with the catalysis.
Maybe while we're waiting, I can take the chair's prerogative. On slide 9, you have this wonderful methylphosphonium, and I've always been asking the same question over and over again. Can you eliminate the iodide and make the vitibridge and make the
I've put the yellow idea in several grant proposals. It's now one of them that I have some money for. Anna, before she left, made the Wittig reagents. She didn't make a MOPS. We've tried to make we can make we used stabilized ilids, so we've got CH2 CN, so a cyano group there, which makes it easier to deprotonate, and we can make the CH double, the PC double bond. We haven't been able to make a frame up with it.
So you don't get to take that one in slide 9 and cook it and eliminate HI?
No, because then you've got to use like a nasty reagent to get rid of to deprotonate, which would be the wrong pH for the stability of the frameworks. So we really want to make the PC double bond first and then assemble it.
So did you try it?
No, we will. It is a great idea.
Other questions? If not, please join me in thanking our speakers.